Hi, my name is Lydia Gilbert, and I'm a senior majoring in climate meteorology with minors in computer science and Latin. My honors capstone, with my advisor, Professor Jeremy Bassis, is a research project entitled Observing and Modeling Drainage Networks from Supraglacial Lakes on Russell Glacier, West Greenland. Supraglacial lakes are lakes that form on top of ice sheets and glaciers when water melted from the top layer of ice collects in depressions. On the Greenland ice sheet, these superglacial lakes occur in the summer during the melt season, usually between May and August. Once it forms, meltwater can be removed from the ice sheet via two pathways. First, when superglacial lakes fill up and overtop, draining to lower elevations until meltwater runs off the ice. Second, when holes in the ice form that can run deep into the ice, sometimes all the way to the bottom, which are called moulins, and drain meltwater away from the surface. Now, why do we care about superglacial lakes? They are very important to understanding the repercussions of global warming on the ice sheet and how those repercussions will impact other parts of the Earth's system. Superglacial lakes and meltwater dynamics impact for example, the meltwater runoff calculations and ice dynamics in climate models and sea level rise estimations. The goal of this project is to understand and predict the processes associated with superglacial lakes by analyzing satellite observations and constructing a meltwater dynamics model for a section of the Greenland ice sheet near Russell Glacier. The observational data set consisted of a set of 4 images from the 2019 melt season from which I identified lakes using an index. These images came from May 9th, June 10th, July 12th, and August 13th. For the meltwater model, I set the only mechanism for the meltwater removal to be runoff, so there's no functionality for moulins encoded in the model. I used an elevation model from 2018 to represent the ice sheet, and I estimated the meltwater added to the ice sheet from cumulative positive degree days. Positive degree days, aka PDD, are a measure of how much radiative forcing in degrees Celsius an area has received, and I used them in my analysis of both observations and modeling results. So, looking at the left side of the results section, you can see there are a group of 8 graphs that show total lake area on the y-axis and mean lake elevation on the x-axis, overlaid with mean PDD experienced. Each row is a date, starting with May 9th, and then going to June 10th, July 12th, and August 13th. The left column represents observed lakes, and the right column represents modeled lakes. And then this column here represents sort of a map of the observed lakes. So if we look over here on the far left, we can see that lakes form at low elevations as early in the melt season, and then form at higher elevations as the melt season progresses. You can also see that the scatter plot points become darker in color, particularly here at low elevations, indicating that the amount of radiative forcing experienced also increases as the melt season progresses. Looking at these 3 graphs right here, you can see on the map how lakes form, grow, and shrink shrink or disappear entirely once they grow large enough. And if we look at figure 5, right here, this left side, which shows lake area versus mean PDD for all observed lakes, we can see that large lakes only have small PDD values. This means that once lakes receive enough radiative forcing, i.e. meltwater, they don't grow anymore and shrink. So either lake overtopping or moulins, or both, must be responsible for this phenomenon. Now, if we take a look at the middle column here, the model results, we can see that they do not match the observations. Late in the melt season, the model overestimates the lake coverage by a large margin. Although I think the model does a pretty good job of estimating the distribution of lake area by elevation. It struggles to drain lakes at a low elevation, so you get sort of like a pile up of meltwater at low elevations. Those are the ones that in observation shrank or dried up once they hit a certain size. The model does not reproduce this sort of lake area like size relationship very well, As you can see in this part of the other part of figure 5, this shows modeled lake area versus mean PDD, because it says here that as lake area increases, so does the radiated forcing, which does not match the patterns in the observation. Therefore, since the model with drainage alone did not reproduce observations, moulins must be responsible for lake coverage reduction once lakes grow too large. In conclusion, results from the observational and model analyses suggest that moulins are a critical mechanism for meltwater removal off the ice sheet and reduction in lake area. They must be accounted for in climate models and sort of considering how meltwater gets off the ice sheet. I started this project the summer before my sophomore year, after I was part of a 2-week expedition to Greenland that was designed to give undergraduates field research experience. This is where I met my research advisor, Jeremy Bassis. My experiences in Greenland and witnessing the effects of climate change on the polar regions firsthand inspired me to ask Professor Bassis if he had any open research projects where I could get involved. He had one he was considering about a supraglacial lake model, and I've been working on it ever since. I faced several challenges working on this project, including the transition to fully virtual only 6 months in. It was definitely more difficult to work on this project when I didn't have the work-life divide anymore. I still found time to work on it and accepted that I might not get as much done as I wanted to before I graduated. One particular problem I faced on this project was that 2 years in, I decided to update the elevation model and the temperature data, which is how I get the positive degree day values, to be more representative. Because of this, I had to redo all the observational and modeling output data and reanalyze my results. It set back my timeline for writing up my results and created a few problems with the model output. I don't regret it though, because it caused me to take a step back and really look at the project and the results I was finding. I ended up pruning some of my analyses that I couldn't get any clear conclusions from, and designed some new ones that gave me a clearer picture of supraglacial lake formation and drainage patterns. I do wish that I had more time to add moulins to my meltwater model and see how that would change the model results, but I think acquiring more accurate data to do my observational analysis and draft my model was a better use of time. All that I've learned on this project about sort of longer-term research, modeling, data analysis, and science communication I will put to good use this fall as I start my PhD at CU Boulder in atmospherics and polar science. I want to say thank you to my advisor Jeremy for all his guidance, enthusiasm, and mentorship these past years.